What if I told you that there's an object so deadly, so incomprehensibly dangerous, that it could destroy everything we know about physics, reality itself, and the very fabric of space-time? What if I told you that this object is real, confirmed by mathematics, and that we've actually detected evidence of its existence? And here's the kicker. It's not just deadly in the way a bomb is deadly, or the way radiation is deadly. No, this object is so dangerous that it literally erases information from the universe, which according to the laws of physics should be impossible. I'm talking about a black hole, but not just any black hole. I'm talking about the most extreme, most dangerous version that could possibly exist. A maximally rotating supermassive black hole at the moment it's consuming matter at the fastest possible rate. And before you think, oh, I already know about black holes, let me stop you right there. Because what I'm about to reveal to you over the next 3.5 hours will completely shatter everything you thought you knew about these cosmic monsters. Here's what will blow your mind. Black holes aren't just dangerous because of their gravity. That's the kindergarten version. Black holes are dangerous because they might be the one place in the ocean universe where the fundamental laws of physics break down completely, where causality itself can be violated, where the future can affect the past, where you could, theoretically, become your own grandfather. Stephen Hawking was so disturbed by what black holes imply about reality that he spent the last 40 years of his life trying to prove they couldn't exist in the form we think they do. He failed, and that failure might be the most terrifying scientific discovery of the 20th century. But here's where it gets even more mind-bending. According to calculations by physicist Kip Thorne in 1986, if you could somehow survive approaching a rotating black hole, you wouldn't just be torn apart by gravity. You'd experience something far stranger. Time would start flowing in circles. Space would become time, and time would become space. The very concepts of before and after would lose all meaning. And if quantum mechanics is correct, the information that makes up you, every thought, every memory, every atom, might not just be destroyed. It might be smeared across the event horizon forever, experiencing every possible moment of your death simultaneously for all eternity. Sleep well tonight. Before we dive deeper into this nightmare, I need you to do something. Hit that like button right now, because this video took months of research, and the algorithm needs to know you want more content like this. Subscribe if you haven't already, because we're going to be exploring the darkest corners of physics together. And drop a comment telling me, what country are you watching from, and what time is it where you are? I want to know where in the world people are brave enough to contemplate cosmic horror at whatever ungodly hour you're watching this. Are you watching this at 2 a.m., unable to sleep? Perfect. You won't be sleeping after this anyway. Now, let's start building your understanding from the ground up. Because to truly appreciate why black holes are the deadliest objects in existence, we need to understand what makes them fundamentally different from everything else in the universe. And trust me, the foundation we're about to build will make the revelations to come even more mind-shattering. Think of the universe as a game with rules. Gravity is a rule. Electromagnetism is a rule. The speed of light is a rule. For the most part, everything in the universe plays by these rules. Stars play by the rules. Planets play by the rules. Even the most extreme cosmic events, like supernovas, play by the rules. They might bend the rules to their breaking point, but they don't break them. Black holes are different. Black holes are what happens when the universe's rulebook gets shredded, burned, and scattered to the cosmic winds. They're not just rule breakers. They're the place where the rules stop applying entirely. Let's start with something basic. Density. You know what density is, right? How much stuff is packed into how much space? Water is denser than air. Lead is denser than water. A neutron star, one of the densest objects we knew about before we understood black holes, has a density so extreme that a teaspoon of its material would weigh about 1 billion tons on Earth. That's already insane. But here's where it gets interesting. A black hole has infinite density at its center. Not really, really high density. Not the highest density we can measure. Infinite density. Literally all of the mass compressed into a point with zero volume. Mathematicians call this a singularity, and it's a fancy word for the math breaks down here, and we have no idea what's actually happening. But here's what most people don't realize. The deadly part of a black hole isn't actually the singularity. The singularity is the final destination, the end of the line. The truly dangerous part is something called the event horizon. And to understand why the event horizon is so terrifying, we need to talk about what it really means, because pop science has been lying to you about event horizons for decades. You've probably heard that the event horizon is the point of no return, or the boundary where escape velocity equals the speed of light. That's technically true, but it misses the profound weirdness of what's actually happening there. The event horizon isn't just a boundary in space. It's a boundary in space-time itself. And this is crucial. Once you cross it, every direction you can possibly move leads toward the singularity. Not because the gravity is pulling you, but because the fabric of space-time itself has been so warped that away from the singularity ceases to be a direction that exists. Think of it like this. Imagine you're walking on Earth. North, south, east, and west are all directions you can walk. Now imagine you're at the North Pole. Suddenly, there's no such thing as north anymore. Every direction is south. The event horizon is like that, except instead of directional coordinates, it's time itself that gets warped. Once you cross the event horizon, every moment of your future leads to the singularity. Not because you can't turn around, but because toward the singularity becomes the only direction that time flows. The singularity isn't in your future because you're falling toward it. You're falling toward it because it's literally the only future that exists. And here's the revelation that should make your brain hurt. This means that inside a black hole, time and space switch roles. Outside a black hole, you can move freely through space, but you're dragged inevitably forward through time. Inside a black hole, you can move freely through time, or you would if you survived, but you're dragged inevitably through space toward the singularity. The singularity isn't a place. It's a moment. It's not waiting somewhere inside the black hole. It's waiting someone. It's the moment when your timeline ends. Now, this was all figured out theoretically by a physicist named Carl Schwarzschild in 1916, just months after Einstein published his theory of general relativity. And here's something incredible. Schwarzschild figured this out while serving in the German army during World War I, calculating the mathematics of curved spacetime in the trenches between artillery barrages. He died shortly after from an autoimmune disease, never knowing that his equations would describe some of the most extreme and terrifying objects in the cosmos. His math predicted that these objects could exist, but for decades, physicists, including Einstein himself, thought they were just mathematical curiosities, impossible monsters that the universe would never actually create. They were wrong. We now know that black holes are not only real but common. There's a supermassive black hole at the center of nearly every large galaxy, including our own. The one at the center of the Milky Way, called Sagittarius A*, has a mass of about 4 million times our Sun. But mass isn't what makes a black hole deadly. What makes it deadly is what happens to the fundamental structure of reality in its vicinity. And to understand that, we need to talk about something called tidal forces, but not the way you've heard about them before. You know what tides are, right? The moon pulls on Earth's oceans, creating high and low tides. That's because the side of Earth facing the moon feels slightly stronger gravity than the far side. The moon is pulling harder on the near side, so water bulges toward it. Simple. Now imagine that instead of the gentle pull of the moon, you're experiencing the gravity of a black hole. The difference in gravitational pull between your head and your feet wouldn't be gentle. It would be so extreme that you'd be stretched like taffy. Physicists have a delightfully morbid term for this: spaghettification. But here's what makes this truly horrifying. The size of a black hole determines how quickly spaghettification happens. For a small black hole, maybe a few times the mass of the sun, the tidal forces at the event horizon are so extreme that you'd be torn into subatomic particles before you even realized you'd crossed the point of no return. Your death would be instantaneous and absolute. But for a supermassive black hole, the kind with millions or billions of solar masses, the event horizon is so far from the center that the tidal forces there are actually pretty gentle. You could cross the event horizon of a supermassive black hole and not even notice. You'd be doomed. You'd have crossed the point of no return. Every second of your remaining existence would be counting down to your inevitable encounter with the singularity. But you could have minutes, maybe even hours, to contemplate your fate. And this is where it gets psychologically terrifying in a way that no other death in the universe could match. Imagine knowing, with absolute certainty, that you are going to die, that there is no escape. Not because you're out of options, but because the universe itself has run out of options for you. Every direction leads to your death. Every second that passes is a second closer to your annihilation. You can try to fire your rocket engines, try to flee in any direction, but all you'd be doing is changing the length of time you have left. The destination is fixed. The singularity is your future, as certain as tomorrow's sunrise, except there won't be a tomorrow after that. And we haven't even gotten to the really scary part yet. What I'm about to tell you is going to sound like science fiction, but it's based on rigorous mathematical physics developed by some of the greatest minds of the 20th century. In 1963, a New Zealand mathematician named Roy Kerr solved Einstein's field equations for a rotating black hole. Remember, the Schwarzschild solution from 1916 was for a non-rotating black hole, a perfect sphere of warped space-time. But real black holes, the ones that actually form in nature, are rotating. They have to be, because the stars they form from are rotating, and that rotation, that angular momentum, is conserved. You can't just make it disappear. Kerr's solution revealed something that shocked the physics community. Inside a rotating black hole, the singularity isn't a point. It's a ring singularity. And here's where reality gets weird enough to make you question everything. Kerr's equations suggested that if you could somehow pass through the ring without touching it, you wouldn't be destroyed. Instead, you'd emerge into a region where the laws of physics as we understand them completely break down. A region where space and time become so twisted that closed time-like curves become possible. That's physicist speak for time travel. Backward time travel. Let me be clear. We don't know if the interior of a rotating black hole actually looks like this. The math says it should, but the math also says that quantum effects we don't fully understand might change everything at the singularity. But if Kerr's solution is even partially correct, then black holes aren't just deadly. They're doorways to regions of spacetime where causality itself becomes optional, where effects can precede causes, where the future can influence the past. And that's just the beginning of the nightmare. Here's something that will keep you up at night. According to quantum mechanics, nothing can be truly destroyed. Information, the fundamental quantum information that describes the state of every particle in the universe, has to be conserved. Always. This isn't just a rule. It's one of the most fundamental principles of physics, right up there with the conservation of energy. If you burn a book, the information isn't destroyed. It's just scrambled into the smoke and ash and heat. Given perfect knowledge and infinite computing power, you could theoretically reconstruct the book from the smoke. That's how deeply physics is committed to information conservation. But what happens to information that falls into a black hole? This question, first posed seriously by Stephen Hawking in the 1970s, created what's now called the black hole information paradox, and it's one of the deepest unresolved problems in theoretical physics. It goes like this. Hawking proved, using quantum mechanics, that black holes aren't completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This means black holes slowly evaporate, losing mass over time. Given enough time, trillions upon trillions of years, a black hole will completely evaporate, leaving nothing but a faint wash of thermal radiation. But here's the problem. Thermal radiation is random. It contains no information. It's like the difference between a book and a fire. The book contains information. The fire is just heat. If a black hole evaporates into thermal radiation, what happened to all the information about everything that ever fell into it? All the stars, planets, people, thoughts, memories, every bit of data encoded in every atom that ever crossed the event horizon. If that information is truly gone, then quantum mechanics is wrong, and one of the most successful theories in the history of science, a theory that's been tested to incredible precision, is fundamentally broken. Hawking himself spent decades trying to resolve this paradox. Other physicists proposed wild solutions. Maybe the information is encoded in subtle correlations in the Hawking radiation. Maybe it's preserved in extra dimensions we can't perceive. Maybe it's stored on the event horizon itself, in a holographic representation that makes no intuitive sense, but might be mathematically consistent. In 2004, Hawking conceded a famous bet and admitted he was probably wrong about information being destroyed, but he couldn't explain where it went. He died in 2018 without resolving the paradox he created. The black hole information paradox isn't just an academic puzzle. It's a fundamental question about the nature of reality. If black holes can destroy information, then the universe isn't deterministic. The future isn't encoded in the present, and physics as we understand it is missing something profound. And that something might be deadly in ways we can't even imagine. But let's bring this back to something concrete, something viscerally terrifying that you can visualize. Let's talk about what happens when matter falls into a black hole at the speeds and densities we actually observe in nature. Because while the theoretical physics is mind-bending, the practical reality is nightmare fuel. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, specifically the supermassive black hole at the center of the M87 galaxy. This black hole has a mass of 6.5 billion times our Sun. That image, that blurry orange ring that captivated the world, was showing us something extraordinary, the photon sphere. This is a region just outside the event horizon where space-time is so warped that light can orbit the black hole. Photons, particles of light, moving at the cosmic speed limit, are bent into circular paths by the extreme curvature of space. But here's what that image doesn't show you, what it can't show you: the accretion disk. Most black holes in the universe are surrounded by disks of matter spiraling into them, and this matter is heated to millions of degrees by friction and compression. We're talking temperatures that make the surface of the sun look cool by comparison. Matter in an accretion disk is moving at significant fractions of the speed of light, and when particles collide at those speeds, they don't just get hot. They emit X-rays and gamma rays, the most energetic forms of electromagnetic radiation in the universe. Now imagine you're approaching this black hole. Forget about the event horizon for a moment. You'll never make it that far. The radiation from the accretion disk would kill you long before you got close to the point of no return. We're not talking about getting a sunburn. We're talking about being bombarded by radiation so intense that it would rip apart your DNA, ionize your atoms, and reduce you to plasma in seconds. And if by some miracle you survived the radiation, you'd still have to contend with the matter in the accretion disk itself. Chunks of former stars, compressed and superheated, moving at relativistic speeds. Being hit by even a small piece of that material would release more energy than a nuclear bomb. This is what makes black holes not just theoretically deadly, but practically deadly. They're not sterile mathematical objects floating peacefully in space. They're surrounded by some of the most violent, energetic, and hostile environments in the entire universe. The jets that some black holes produce, streams of matter and energy ejected along their rotational axes, can extend for millions of light years and contain more energy than entire galaxies. If one of these jets were pointed at Earth, even from thousands of light years away, it would sterilize our planet, stripping away our atmosphere and oceans, and leaving nothing but a dead, irradiated rock. And here's something that should terrify you. We don't fully understand what triggers these jets or how they're powered. We think it has something to do with the interaction between the black hole's rotation, the accretion disk, and powerful magnetic fields, but the details are still being worked out, which means there could be even more dangerous phenomena associated with black holes that we simply haven't discovered yet. Let me throw another mind-bending fact at you: time dilation. You've probably heard that time moves slower in stronger gravitational fields, right? That's a consequence of general relativity, and it's been tested experimentally. GPS satellites have to account for it, or your navigation would be off by miles. But near a black hole, this effect becomes extreme. If you were watching someone fall into a black hole from a safe distance, you'd never see them actually cross the event horizon. You'd see them slow down, their movements becoming more and more sluggish, their light shifting to redder and redder wavelengths, until they appeared to freeze at the event horizon itself, fading from view as their light was stretched to infinitely long wavelengths. But from their perspective, from the perspective of the person falling in, nothing strange happens at the event horizon. They cross it at a definite moment. Time continues to pass normally for them, at least until the tidal forces become extreme. So which perspective is real? Are they frozen at the event horizon or falling through it? The answer, the deeply unsatisfying answer that physics gives us, is both. Both perspectives are equally valid, equally real, just measured from different reference frames. The person falls through, and the person freezes at the horizon simultaneously from different points of view. Reality itself becomes relative, observer-dependent, split into irreconcilable perspectives. And if that doesn't make you question the nature of reality itself, I don't know what will. Think about the implications. If reality is observer-dependent near a black hole, if there's no single objective truth about what's happening, then what does that mean for the nature of the universe? Is reality just a collection of different perspectives, all equally valid, with no deeper underlying truth? Or is there some more fundamental description that unifies all these perspectives, some theory of quantum gravity that we haven't discovered yet? These aren't just philosophical questions. They're questions about the actual structure of the universe, and black holes are the places where these questions become unavoidable. Now, I promised you that this video would get progressively more mind-bending, and we're about to kick it into a higher gear. Because everything I've told you so far, as strange and terrifying as it is based on classical general relativity. Einstein's theory, as revolutionary as it was, is incomplete. It doesn't account for quantum mechanics. And when you try to combine general relativity with quantum mechanics near a black hole, things get weird. Weirder than anything I've described so far. We're about to enter territory where our best theories contradict each other, where the math suggests things so bizarre that even physicists have trouble accepting them, where the very concept of object or place or moment starts to break down. Stay with me, because what comes next will change how you see the universe forever. But before we go there, take a moment, breathe, look around your room. Notice that space is three-dimensional, that time flows in one direction, that causality seems to work normally. Appreciate it, because we're about to explore the places where all of that breaks down. And there's no turning back from here. You still with me? Good, because we need to talk about what happens when quantum mechanics enters the picture, and why that makes black holes even deadlier than classical physics suggests. But to get there, I need to introduce you to one of the strangest features of quantum mechanics, something that even Einstein found so disturbing, he spent years trying to prove it couldn't be real. I'm talking about quantum entanglement. Here's the basic idea. In quantum mechanics, Particles don't have definite properties until they're measured. An electron doesn't have a definite position or a definite momentum. It exists in a superposition of all possible positions and momenta until you observe it. That's the famous uncertainty principle, and it's been experimentally verified thousands of times. But entanglement goes further. Two particles can be entangled, meaning their properties are correlated in ways that seem impossible. Measure the spin of one particle, and you instantly know the spin of the other, even if they're on opposite sides of the universe. Einstein called this spooky action at a distance, and thought it proved quantum mechanics was incomplete. He was wrong. Experiments by physicist Alan Aspect in the 1980s and many others since have confirmed that entanglement is real. Particles really can be connected across vast distances in ways that seem to violate the principle that nothing can travel faster than light. I say seem to because technically no information is being transmitted. The correlation was established when the particles were created, but it's still deeply weird, and it has profound implications for black holes. In the 1990s, physicist Leonard Susskind proposed something called the holographic principle, and it's one of the most radical ideas in modern physics. The principle states that all the information contained within a region of space can be described by information encoded on the boundary of that region. It's like how a hologram, a two-dimensional surface, can contain information about a three-dimensional image. Applied to black holes, this suggests that all the information about everything that ever fell into a black hole isn't actually inside the black hole at all. It's encoded on the event horizon itself. Think of it like this. Imagine the event horizon is like the surface of a hard drive, and everything that falls in, it's written to that surface as data. From outside the black hole, the information is still there, scrambled but not destroyed, encoded in microscopic quantum structures on the horizon. But from inside the black hole, the information has genuinely fallen in and is heading toward the singularity. Both descriptions are correct, just from different perspectives, and this duality might be the key to resolving the information paradox. But here's where it gets truly mind-bending. If the holographic principle is correct, then it applies not just to black holes, but to the entire universe. The three-dimensional reality you perceive might be a holographic projection of information encoded on a two-dimensional boundary at the edge of the observable universe. You, me, everything we see and touch and feel might be holographic projections. The real information might exist in a form we can't directly perceive, and what we think of as three-dimensional reality might be an emergent phenomenon, like how a 3D image emerges from a 2D hologram. Now, I know what you're thinking. This sounds like science fiction, like The Matrix, like simulation theory. And you're right to be skeptical. But this isn't fringe physics. This is a serious proposal that emerged from trying to reconcile general relativity with quantum mechanics, and it's taken seriously by some of the best physicists in the world. We don't know if it's true, but the fact that black holes force us to even consider possibilities like this shows just how fundamentally strange these objects are. Let me give you another example of how quantum effects make black holes even weirder. Remember Hawking radiation, the thermal radiation that black holes emit? Here's what's actually happening, as best as we understand it. Quantum mechanics tells us that empty space isn't really empty. It's filled with pairs of virtual particles, constantly popping in and out of existence, borrowing energy from the vacuum for tiny fractions of a second before annihilating each other. Normally, these particles exist for such a short time that they can't be observed directly. They're a quantum fluctuation, a temporary loan against the energy of the vacuum that gets immediately paid back. But near a black hole's event horizon, something different can happen. A pair of virtual particles can pop into existence right at the horizon. One particle falls into the black hole before it can annihilate, and the other particle escapes. To an outside observer, it looks like the black hole emitted a particle. But here's the catch. The escaping particle has positive energy, which means the particle that fell in must have had negative energy relative to an outside observer. The black hole has absorbed negative energy, which means it's lost mass. This is why black holes evaporate. But think about how absolutely bizarre this process is. The black hole is losing mass by absorbing particles. It's being destroyed by things falling into it. And the radiation it emits is random, thermal, containing none of the information about what fell in. This is the heart of the information paradox, and it suggests that something deeply strange is happening at the quantum level near event horizons. Some physicists, including Hawking himself before he changed his mind, thought this meant that black holes are the one place where information can be destroyed, where quantum mechanics breaks down. Others proposed that maybe the evaporating black hole leaves behind a remnant, a tiny quantum object that somehow contains all the information about everything that ever fell in, compressed into something smaller than an atom. But this creates its own problems. How can a tiny remnant contain an arbitrarily large amount of information? The math suggests it would collapse into yet another black hole, creating an infinite regress of black holes inside black holes. The resolution might be even stranger. Maybe information isn't lost or preserved in a remnant. Maybe it's been encoded in the Hawking radiation all along, in correlations so subtle and complex that we don't yet know how to detect or decode them. This would require that the Hawking radiation isn't truly thermal, that it contains hidden information in quantum correlations between particles emitted at different times. Recent calculations suggest this might be possible, but the details are still being worked out. And here's why this matters. Why this isn't just an abstract problem for physicists to worry about. If black holes can destroy information, then the future isn't determined by the past. Two identical initial states could lead to different final states, with the difference being what got destroyed by a black hole. This would mean that physics is fundamentally random at the deepest level, that there's no equation, no matter how complete, that could predict the future from the present. The universe would be genuinely indeterministic, and everything we think we understand about cause and effect would be an approximation that breaks down near black holes. But if information is preserved, if black holes don't destroy information, then we need a theory of quantum gravity that explains how. And every attempt to create such a theory leads to implications almost as bizarre as information destruction itself. String theory, one of the leading candidates, requires that space has 10 or 11 dimensions, most of which are curled up so small we can't detect them. Loop quantum gravity suggests that space isn't continuous, but is made of discrete chunks, and that the singularity inside a black hole might actually be a bounce to another region of spacetime. These aren't minor modifications to physics. These are complete overhauls of our understanding of reality. And black holes are the laboratories where these theories are tested, where the predictions of quantum gravity would be most visible, if only we could see inside the event horizon. Now let me tell you about something that will make you appreciate just how deadly black holes are in practical terms: tidal disruption events. When a star wanders too close to a supermassive black hole, something extraordinary happens. There's a point, called the tidal radius, where the tidal forces from the black hole overcome the star's own gravity. The star doesn't just fall in whole. It gets stretched, pulled apart like taffy, until it's no longer a coherent object, but a stream of plasma spiraling into the black hole. Astronomers have observed these events, and they're spectacular. The infalling material heats up to millions of degrees and emits enormous amounts of X-rays and visible light. For a few weeks or months, a black hole that was previously quiet can suddenly become one of the brightest objects in the sky, outshining entire galaxies. Then, as the disrupted star is consumed, the light fades, and the black hole goes quiet again until the next victim wanders too close. But here's what gets me about these events. The star never sees it coming. Or rather, it does, but there's nothing it can do. Stars don't have brains or consciousness, obviously, but if they did, the star would realize it was doomed long before the tidal forces became extreme. Once you're within the tidal radius, there's no escape. You can't speed up, can't change course, can't do anything but wait for the inevitable destruction. And because of time dilation, from the perspective of an outside observer, the final moments of the star's death are stretched out over weeks or months, a slow-motion catastrophe playing out in X-rays and ultraviolet light. Now imagine, just for a moment, that instead of a star, it's a planet with a civilization. They would have time to see it coming, to understand what was happening, to know with absolute certainty that their world was going to end, and there was nothing they could do about it. They couldn't evacuate. Where would they go? They couldn't fight back. You can't fight geometry itself. They would just have to watch as their sky grew brighter and hotter, as tides began to tear their world apart, as the ground beneath their feet began to stretch and crack, as their atmosphere was stripped away into space, as everything they ever knew or built or cared about was reduced to plasma and consumed by the void. That's the existential horror of black holes. They're not just deadly in the sense of killing you quickly. They're deadly in the sense of inevitable doom, unstoppable destruction, the complete and utter negation of everything. And there's nothing, absolutely nothing, that any amount of technology or intelligence could do to prevent it once you're caught. The laws of physics themselves become your executioner. And we haven't even talked about the most extreme types of black holes yet. Remember when I mentioned rotating black holes, the Kerr solution? Well, there's a theoretical limit to how fast a black hole can spin, set by the requirement that the event horizon still exists. Spin a black hole too fast, and according to the math, the event horizon disappears, exposing the singularity to the outside universe. This hypothetical object is called a naked singularity, and most physicists believe they can't exist. There's even something called the cosmic censorship hypothesis, proposed by Roger Penrose in 1969, which states that all singularities must be hidden behind event horizons. But we don't know if cosmic censorship is true. We hope it's true, because naked singularities would be even worse than black holes. At least with a black hole, the breakdown of physics is safely hidden away where it can't affect the outside universe. A naked singularity would be a point of infinite density and infinite curvature visible to the cosmos, a place where the laws of physics break down completely and causality ceases to have meaning, broadcasting its wrongness to the entire universe. If naked singularities could exist, they would be the deadliest objects imaginable, singularities in physics itself, tears in the fabric of reality that could potentially cause unpredictable effects across vast distances. Fortunately, every simulation we've run, every observation we've made, suggests that cosmic censorship holds. When a star collapses, it forms an event horizon. When black holes merge, they maintain their horizons. The universe seems to protect itself from naked singularities, hiding its breakdowns of physics from view. But the fact that we have to hope for this, that it's a hypothesis rather than a proven theorem, should give you pause. Our understanding of black holes is still incomplete, and there might be situations we haven't thought of where the rules break down in new and terrifying ways. Speaking of merging black holes, let's talk about what happens when two black holes collide, because this is one area where theoretical physics and observational astronomy have come together in spectacular fashion. In 2015, the LIGO collaboration detected gravitational waves for the first time, ripples in spacetime itself, caused by two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. This observation won the Nobel Prize in 2017, and for good reason. It confirmed a prediction Einstein made 100 years earlier and opened up an entirely new way of observing the universe. But focus on what that event actually represents. Two black holes, each carrying the mass of dozens of suns, orbiting each other at significant fractions of the speed of light, getting closer and closer until finally they merge. In the final seconds before merger, they're emitting more power and gravitational waves than all the stars in the visible universe combined emit in light. More power than every star, every galaxy, every source of electromagnetic radiation in the observable universe, all concentrated in two objects each smaller than a city, all released as vibrations in the geometry of space and time itself. And in that final moment, as they merge, about 3 solar masses of energy is converted directly into gravitational waves, according to E equals mc. 3 suns worth of mass just vanishes, transformed into ripples in space-time that wash over the universe at the speed of light. The resulting black hole has less mass than the 2 original black holes combined. Mass was destroyed, converted to energy, and radiated away as gravitational waves. Now think about being near such an event. Not right next to it, obviously. You'd be destroyed. But imagine being a few light years away, far enough that you'd survive, but close enough to detect it. Space-time itself would be rippling, stretching, and compressing by tiny amounts, causing everything around you to oscillate. The distance to nearby stars would be changing by fractions of a proton's width, space itself breathing in and out as the gravitational waves pass through. And this wouldn't be over in an instant. The waves would continue for minutes or hours, depending on how far away you were, as the initial burst was followed by echoes and reverberations, space-time ringing like a bell struck by gods. The most extreme black holes we know of aren't stellar mass black holes like the ones LIGO detected. They're supermassive black holes, the ones at the centers of galaxies, with masses of millions or billions of suns. And these monsters are deadly in ways that go far beyond just swallowing nearby stars. They regulate the evolution of entire galaxies through their feedback effects. When matter falls into them, when they're actively feeding on stars and gas, they emit so much energy that they can heat the surrounding gas to temperatures where star formation becomes impossible. They can blow winds of hot gas out of galaxies, removing the raw material needed to make new stars. In a very real sense, supermassive black holes are responsible for the eventual heat death of galaxies, the slow process by which star formation peters out and galaxies go dark. Our own galaxy's supermassive black hole, Sagittarius A*, is relatively quiet right now, but there's evidence that in the past it's had active periods where it emitted enormous amounts of energy. And it will feed again in the future, potentially when the Andromeda Galaxy collides with the Milky Way in about 4 billion years. The 2 supermassive black holes, ours and Andromeda's, will eventually merge, creating an even larger monster at the center of the merged galaxy. But here's something that should put your life in perspective. You're living in a galaxy with a 4 million solar mass black hole at its center, about 26,000 light years away from you. That's close, cosmically speaking, and yet you're safe. You're safe because space is vast, because gravity falls off with distance, because the black hole isn't reaching out to grab you. You're safe because you're in orbit around the galactic center, along with the sun and all the other stars, circling the central black hole every 230 million years or so. You're safe, for now, because eventually, billions of years from now, long after the sun has died, the Milky Way galaxy will merge with Andromeda. And when that happens, the orderly orbits of stars will be disrupted. Some stars will be flung out of the merged galaxy entirely. Others will fall into the galactic center, potentially into the supermassive black hole. If there's still life on Earth at that point, if Earth even still exists, our descendants or whatever species succeeds, us will watch as the sky transforms. As the Andromeda Galaxy grows larger and larger, as the 2 galaxies interpenetrate and merge, as the black holes at their centers spiral together and merge in a cataclysm that will release more energy than billions of supernovas. And they'll be powerless to stop it, or change it, or do anything but watch. That's the ultimate deadliness of black holes, not just to individuals or planets, or even stars, but to galaxies themselves, to the large-scale structure of the universe. They're the ultimate sinkholes, the final resting places of matter and energy, the points where information goes to die or be transformed into something we don't understand. They're the universe's way of taking back the gift of existence, of reducing complexity back to simplicity, of making sure that nothing lasts forever. But we're not done yet, not even close, because I haven't told you about the most speculative, most controversial, most potentially deadly aspect of black holes, what might lie on the other side. Some solutions to Einstein's equations suggest that black holes might connect to other regions of spacetime through structures called wormholes or Einstein-Rosen bridges. Now, before you get excited about using black holes for faster-than-light travel or time travel, let me immediately pour cold water on that idea. These wormholes, if they exist at all, are unstable. They collapse before anything can traverse them, and they connect to other black holes, other regions of extreme spacetime curvature, not to convenient exits in distant parts of the universe. But the math is intriguing. The equations suggest that the internal structure of rotating black holes might be far stranger than we imagine, with multiple regions of spacetime connected in bizarre ways. Some solutions even suggest the possibility of closed time-like curves, paths through spacetime that loop back on themselves, allowing time travel to the past. This is where physics bumps up against its own limitations, where the math produces answers that seem physically impossible. Here's the thing. These solutions are mathematically valid, but they require exotic conditions that probably don't exist in nature. They require negative energy densities, matter with negative mass, things we've never observed, and that might be forbidden by deeper physical principles we don't yet understand. But the fact that general relativity even allows these solutions, that the equations of our best theory of gravity permit time travel and traversable wormholes under certain conditions, tells us something profound. The universe is far stranger than common sense would suggest. And black holes are the places where that strangeness becomes most apparent. Let me give you a thought experiment that illustrates just how weird causality gets near black holes. Imagine you're orbiting close to a rotating black hole in a region where spacetime is heavily curved, but you're still outside the event horizon. The black hole's rotation drags spacetime around with it, an effect called frame dragging. In the most extreme region, called the ergosphere, frame dragging is so strong that you can't remain stationary relative to distant stars, no matter how hard you try. You're forced to rotate with the black hole, dragged along by the flow of spacetime itself. Now imagine you're in this ergosphere, and you decide to drop something into the black hole. But before you do, you're going to do something clever. You're going to use the black hole's rotation to extract energy. This is called the Penrose process, proposed by Roger Penrose in 1969. Here's how it works. You throw an object into the ergosphere in such a way that it splits into two pieces. One piece falls into the black hole, but the other piece escapes, and because of the frame dragging, the escaping piece can have more energy than the original object. You've extracted rotational energy from the black hole. This isn't science fiction. It's a legitimate process allowed by general relativity. And if we ever develop the technology to get close enough to a rotating black hole, we could theoretically use this process to extract enormous amounts of energy. But here's the deadly part. Doing this slows down the black hole's rotation. And if you extracted all of the rotational energy, you'd be left with a non-rotating Schwarzschild black hole, which has different properties than a Kerr black hole. You'd be changing the fundamental nature of the object itself. And this gets at something important. Black holes aren't static. They evolve. They grow by accreting matter. They shrink by emitting Hawking radiation. They speed up or slow down as they absorb or emit angular momentum. They merge with other black holes. They're dynamic objects, and their properties change over time. The deadliest black hole isn't a fixed target, but a moving one, literally and figuratively. The danger it poses changes depending on its state, and we're only beginning to understand the full range of behaviors black holes can exhibit. Now, I want to take a moment to address something you might be thinking. Okay, black holes are deadly, but they're far away. They can't hurt me. Why should I care? And that's a fair question. The nearest known black hole to Earth is probably several hundred or thousand light years away. You're in no immediate danger. But I want to push back on that attitude because it misses the profound importance of black holes to our understanding of reality. Black holes are nature's way of showing us the limits of our theories, the places where our understanding breaks down. They're the laboratories where quantum mechanics and general relativity collide, where the smooth fabric of space-time meets the discrete, probabilistic world of quantum fields. And understanding black holes isn't just about understanding strange objects in distant space. It's about understanding the fundamental nature of reality itself. What is time? What is space? What is information? What determines what's possible and what's forbiddenness? These aren't abstract questions. They're questions that affect how we understand ourselves and our place in the universe. They're questions that might have practical applications we can't even imagine yet. Quantum mechanics, after all, started as an abstract mathematical theory about atoms and has given us computers, lasers, MRI machines, and countless other technologies that define modern life. Who knows what technologies might emerge from a complete theory of quantum gravity, from truly understanding what happens inside a black hole. And there's another reason to care, a more philosophical one. Black holes confront us with our own mortality and insignificance in a way few other phenomena do. They're the ultimate reminder that the universe doesn't care about us, that physics continues operating according to its inexorable laws, regardless of our preferences or desires. They're reminders that we're temporary, that everything we build and create and care about is temporary, that on long enough timescales, entropy always wins. But they're also reminders of how far we've come. 100 years ago, black holes were just bizarre solutions to Einstein's equations, mathematical curiosities that most physicists thought couldn't possibly be real. Today, we photograph them. We've detected their gravitational waves. We're using them as laboratories to test our theories. We went from "these can't exist" to "here's a picture of one" in a single century. That's extraordinary. That's a testament to human curiosity, human intelligence, human persistence in the face of mystery. So yes, black holes are deadly. Yes, they're terrifying. Yes, they represent everything that can go wrong when physics is pushed to its limits. But they're also beautiful in a way. Beautiful in the way that a perfectly solved equation is beautiful. Beautiful in the way that a complete understanding of a previously mysterious phenomenon is beautiful. They're the universe showing us what it's truly capable of, the full range of phenomena that can emerge from the elegant simplicity of Einstein's field equations. And we're only beginning to understand them. We're at the halfway point now, and I want to shift gears slightly. We've built up the physics, we've explored the mathematics, we've looked at the observational evidence. Now, I want to bring this back to you personally, to talk about how black holes connect to your life and your understanding of reality, even though you'll probably never get within 1 billion miles of one. Because the implications of black holes extend far beyond astrophysics. They touch on philosophy, on consciousness, on what it means to exist in a universe governed by physical laws. Let's start with a question. What is time? It's such a basic concept that we rarely think about it. Time is just time, right? The thing that flows from past to future, the dimension along which things change. We're so used to time that we take it for granted. But black holes force us to confront the fact that time isn't what we think it is. In everyday experience, time seems universal. When something happens now, it happens now for everyone. But special relativity showed that simultaneity is relative, that different observers moving at different speeds will disagree about what events are simultaneous. General relativity took this even further. Time flows at different rates in different gravitational fields. Near a black hole, time dilation becomes extreme. And inside a black hole, as we've discussed, time and space switch roles. So what is time really? The answer from physics is that time is a coordinate, a dimension of space-time, no more or less fundamental than the 3 dimensions of space. But that doesn't match our experience. We feel like we're moving through time, like the present moment is special in a way that spatial locations aren't. We remember the past, but not the future. We feel like we have agency, like we can make choices that affect what happens next. But if time is just a coordinate, if the entire history of the universe exists as a four-dimensional block of space-time, then the past, present, and future all exist equally. Your birth, your childhood, this moment right now reading this script, your death, all of it exists as a single four-dimensional structure. The flow of time, the feeling that the present moment is special, might be an illusion, a product of how our brains process information rather than a feature of reality itself. This is called the block universe view, and it emerges naturally from relativity. But it's deeply uncomfortable because it seems to rule out free will. If your entire future already exists in the four-dimensional structure of space-time, then how can you make choices? How can the future be open if it's already determined? Black holes make this problem even more acute. Inside a black hole, where time and space trade places, the concept of choosing becomes even more fraught. You're not choosing whether to move toward the singularity any more than you're choosing to move forward in time right now. It's just what happens. The singularity is your future, period, regardless of what you do. The illusion of choice, if it exists outside black holes, is shattered completely inside them. Now, I'm not telling you this to make you feel depressed or nihilistic. I'm telling you this because grappling with these questions, really sitting with the strangeness of what physics tells us about time, can be profound. It can change how you relate to your own life. If the block universe view is correct, then in a very real sense, you'll never actually die. Yes, there are moments in space-time where you exist and moments where you don't, but they all exist equally. The moment of your death is just a boundary, a point where your world line ends, no different in principle from the boundary of any other object in space-time. Alternatively, if time really does flow, if the present moment really is special, then we need to understand why, and black holes might give us clues. Maybe quantum mechanics introduces genuine randomness that makes the future truly open. Maybe consciousness plays a role in collapsing quantum superpositions, making certain futures real and others merely potential. These are speculative ideas, not established science, but they're taken seriously by some physicists precisely because our current theories leave questions about the nature of time unresolved. Let's talk about another personal connection: information and identity. What makes you you? Is it the specific arrangement of atoms in your body? Is it the pattern of neural connections in your brain? Is it your memories, your personality, your continuity of consciousness? These questions become more than philosophical when we consider the black hole information paradox. If information really is preserved when you fall into a black hole, then in principle, everything about you, every atom, every thought, every memory still exists somewhere, somehow. Maybe it's encoded on the event horizon in quantum degrees of freedom we don't understand. Maybe it's preserved in subtle correlations in the Hawking radiation. But it exists. You're not truly destroyed, just transformed into a form that's inaccessible and scrambled beyond recognition. But if information can be destroyed, then there's a sense in which you can be truly erased from the universe. Not just killed, but unmade, with no trace remaining. The information that constituted you, that made you a unique configuration of matter and energy, would be gone forever. Not scrambled, not hidden, but actually destroyed, as though you never existed at all. Which scenario is more terrifying? Eternal existence as scrambled information on an event horizon, or complete erasure? I honestly don't know. Both seem horrifying in different ways. But the fact that black holes force us to think about these questions, to confront the nature of information and identity and existence at the deepest level, is significant. These aren't just physics questions. They're existential questions. Here's another angle. Black holes represent the ultimate limit of prediction. In principle, if we knew the exact state of every particle in the universe, and we had unlimited computing power, We could predict the future, at least in a deterministic universe. This is the dream of Laplace's demon, the hypothetical superintelligence that knows everything and can calculate everything. But black holes complicate this picture. Even if we could measure the state of the universe perfectly, we couldn't predict what comes out of a black hole when it evaporates. At least not in detail, because the Hawking radiation is thermal, random. If information is truly destroyed, then the universe isn't deterministic. Identical initial states can lead to different final states. If information is preserved, but scrambled in unimaginably complex ways, then predicting the future requires understanding quantum gravity at a level we're nowhere close to achieving. Either way, black holes represent the fundamental limit to prediction and control. They're regions where the future becomes inaccessible, not because of practical limitations, but because of the structure of physics itself. And this has implications for how we think about knowledge, control, and power. There are things we can't know, things we can't predict, not because we're not smart enough or don't have good enough instruments, but because the universe itself has limits on what can be known. This should be humbling. It should make us more modest in our claims, more careful in our assumptions, more willing to say, "I don't know," when we reach the boundaries of our understanding. But it should also be inspiring, because it means there will always be mysteries, always be frontiers to explore, always be questions that the next generation of physicists can tackle. The universe will never be fully understood, never be fully predictable, never be completely tamed. And black holes are the proof. Now let me tell you about something called the holographic principle again, but from a different angle. We talked earlier about how the holographic principle suggests that information about the interior of a region can be encoded on its boundary. Applied to black holes, this means the event horizon acts like a holographic screen, but the principle is more general. It might apply to the entire universe. In the most radical version of the holographic principle, our entire three-dimensional universe is a holographic projection of information, encoded on a two-dimensional boundary at the edge of the observable universe. Everything you see, feel, and experience is a 3D hologram projected from a 2D surface. The real physics is happening in 2 dimensions, and the three-dimensional world we perceive is emergent, a kind of illusion. If this is true, then what does it mean for your existence? Are you a holographic projection? Is your consciousness emergent from 2D processes you can't perceive? What does it mean to be real in a holographic universe? These questions sound like they belong in a science fiction novel, but they're being seriously discussed by physicists because of what black holes teach us about the nature of information in space. And here's the kicker. We might be able to test this. If the universe is holographic, there should be subtle signatures in the correlations between quantum fields at very small scales. Experiments are being designed to look for these signatures, to test whether our 3D reality really is a hologram. We might, within our lifetimes, find out that the universe is far stranger than even physicists currently believe. Let me bring this down to earth with a concrete analogy. Think about your life as a story, with a beginning, middle, and end. Most of us think of this story as having free will woven throughout, moments where we made choices that determined how the story unfolded. But the block universe view suggests the entire story already exists, written in the 4-dimensional structure of spacetime. You're not writing the story as you go. You're reading it, experiencing it moment by moment, but it's already complete. Now add black holes to the picture. Black holes are the chapters in the universe's story where the narrative breaks down, where the rules that govern previous chapters stop applying. They're the points where the story becomes self-referential and paradoxical, where the text on the page dissolves into quantum foam and information paradoxes. They're reminders that the story of the universe isn't a nice, linear narrative with a clear plot and resolution. It's strange, self-contradictory, incomplete, and utterly indifferent to making sense to human minds. And yet, we persist in trying to understand it. We persist in building theories, running experiments, making observations, slowly piecing together a picture of how the story works even as we're embedded in it, even as we're made of the same stuff the story is about. That's remarkable. That's worth celebrating, even as we acknowledge how little we actually understand. Let's talk about scale for a moment, because I think it will help put your place in the universe in perspective. You're sitting somewhere on Earth, a planet about 12,000 kilometers in diameter. Earth orbits the Sun, a star about 1.4 million kilometers in diameter, at a distance of about 150 million kilometers. The Sun is one of about 200 billion stars in the Milky Way galaxy, which is about 100,000 light-years across. And the Milky Way is one of trillions of galaxies in the observable universe, which is about 93 billion light-years across. At the center of the Milky Way is Sagittarius A, asterisk, a black hole with a mass of 4 million suns, but a physical size. At its event horizon of only about 44 million kilometers across, smaller than the orbit of Mercury. Think about that. An object with the mass of 4 million stars, compressed into a region smaller than Mercury's orbit. The density, the curvature of space, the sheer roundness of it, is hard to even contemplate. Now zoom out. In the observable universe, there are probably billions of supermassive black holes, one at the center of nearly every large galaxy. There are probably trillions or quadrillions of stellar mass black holes, the remnants of massive stars that died long ago. And these are just the black holes we think exist, based on our current understanding. There might be other populations we haven't discovered yet. Primordial black holes formed in the early universe, intermediate mass black holes that don't fit into the stellar or supermassive categories, even microscopic black holes, if certain quantum gravity theories are correct. The universe is full of these deadly objects, these regions where physics breaks down and information goes to die. They're not rare anomalies. They're common, ordinary features of the cosmic landscape. And yet life exists. You exist. In a universe full of black holes, in a galaxy with a supermassive black hole at its center, on a planet orbiting a star that will eventually die, in a cosmos that is slowly marching toward heat death, you are here, aware, thinking, trying to understand. That's astonishing. That's defiant in a way. The universe is vast, and old and full of dangers, and ultimately doesn't care about you. But here you are anyway, reading this, learning about black holes, expanding your understanding. The fact that conscious, intelligent beings emerged in this universe, beings capable of understanding black holes, even if only partially, is a kind of miracle. It's certainly improbable. And it's beautiful. So when I say black holes are the deadliest objects in the universe, I'm not just talking about their capacity to destroy matter and energy. I'm talking about how they challenge our understanding, how they confront us with the limits of our knowledge, how they remind us that the universe is not here for us, does not care about us, and operates according to laws that are sometimes brutal in their simplicity and indifference. Black holes are deadly to our pretensions, to our sense that we understand the world, to our comfort. But they're also invitations. Invitations to think more deeply, to question more carefully, to explore more bravely. Every question we answer about black holes leads to 10 new questions. Every mystery we solve reveals deeper mysteries, and that's good. That's as it should be. A universe we fully understood would be boring. A universe that kept no secrets would offer no adventures. Black holes keep secrets, deep secrets. Secrets about the nature of time and space and information and reality itself. And we're slowly, painstakingly, learning how to interrogate those secrets, how to tease out answers even from objects that seem designed to hide information forever. Now, here's something I want you to do. Stop for a moment and think about your day tomorrow. You'll wake up, go about your routine, interact with people, do work or school or whatever your life involves. Time will flow in one direction. Causality will work normally. Space will have 3 dimensions, and nothing will seem particularly strange. And that's okay. That's normal. That's how life should be. But I want you to remember that underneath that everyday normality, underneath the familiar world of experience, there's something far stranger going on. Space and time are part of a unified fabric that can be bent and stretched. Matter and energy are different forms of the same thing. Information is a physical quantity that must be conserved. And out there in the cosmos, there are objects so dense, so massive, so extreme that they break the rules entirely, creating regions where everything we take for granted stops being true. You're living in a universe with black holes in it. That should change how you see things, at least a little bit. It should make you appreciate how strange reality is, how lucky you are to exist in a region of space-time where physics works normally, where time flows forward and space is space, and causality makes sense. It should also make you curious. Because if black holes can exist, if physics allows objects this strange and extreme, what else is possible? What other bizarre phenomena are hiding in the equations, waiting to be discovered? What other ways can reality surprise us? The universe is a stranger place than you think, and black holes are here to prove it. Let me tell you about some cutting-edge research that's happening right now as we speak. Research that might revolutionize our understanding of black holes in the next few decades. There are multiple experiments and observations underway that are pushing the boundaries of what we can learn about these objects. First, there's the Event Horizon Telescope, which produced that famous first image of a black hole's shadow in 2019. They're not stopping there. They're adding more radio telescopes to their network, improving resolution, and planning to capture images of multiple black holes, including Sagittarius A*, at the center of our own galaxy. With each new image, we'll learn more about how matter behaves in extreme gravitational fields, how black holes interact with their surroundings, and whether general relativity's predictions hold up in these extreme environments. Second, there's the Laser Interferometer Space Antenna, or LISA, a planned space-based gravitational wave detector that will launch in the 2030s. Unlike LIGO, which detects gravitational waves from stellar mass black hole mergers, LISA will detect waves from supermassive black hole mergers, events so energetic they shake the fabric of space-time across the entire universe. These observations will tell us how supermassive black holes formed, how they grew, and how common they are throughout cosmic history. Third, there's theoretical work on the black hole information paradox. Physicists are making progress on understanding how information might be preserved in Hawking radiation through quantum entanglement effects. Recent work suggests that the interior and exterior of a black hole might be connected in ways far more complex than we imagined, with information gradually leaking out as the black hole evaporates. This research is bringing together string theory, quantum field theory, and general relativity in ways that might finally give us a theory of quantum gravity. And fourth, there are observations of stars orbiting close to Sagittarius A*, our galaxy's central black hole. Astronomers have been tracking these stars for decades, measuring their orbits with increasing precision. In 2018, one of these stars, called S2, passed within 17 light hours of the event horizon, traveling at about 3% the speed of light. Observations of this passage confirm general relativity's predictions about time dilation and gravitational redshift in strong gravitational fields. Future observations of even closer passages might reveal deviations from general relativity that would point toward a theory of quantum gravity. All of this is happening now. This isn't ancient history. This is ongoing research at the cutting edge of physics and astronomy. And it's accelerating. The rate at which we're learning about black holes is faster now than at any point in history. And it's only going to get faster as new instruments come online and new theoretical insights emerge. What does this mean for you? It means that the picture I've painted in this video is incomplete and will be obsolete in ways we can't predict within a decade or two. It means that if you're young enough, you'll live to see major breakthroughs in our understanding of black holes, discoveries that might overturn much of what we currently believe. It means that the story of black holes is still being written, and you get to watch it unfold. But let's bring this back to something personal one more time. I've spent hours now telling you about black holes, about their danger, their strangeness, their implications for physics and philosophy, and our understanding of reality. And you might be wondering, what's the point? Why should I care about objects I'll never see up close, phenomena I'll never experience, physics that has no practical impact on my daily life? Here's my answer: because this is your universe. These are the rules you're living under, the laws that govern every atom in your body, every photon entering your eye, every thought in your mind. Understanding black holes, even if only at a surface level, is part of understanding reality. And understanding reality, deeply and truly, is one of the most worthwhile things a human can do. We live in an age where most people will go their entire lives without thinking deeply about the cosmos, about the nature of space and time, about where the universe came from or where it's going. They'll live in a bubble of everyday concerns, and that's fine. That's normal. But it's also a tragedy, because they're missing out on something profound: the knowledge that we are part of something vast and ancient and strange, that we are made of atoms forged in stars, that we live on a planet orbiting one of hundreds of billions of stars in a galaxy that's one of trillions of galaxies, and that out there in the darkness are objects so extreme they defy comprehension. Knowing about black holes, really knowing about them, changes you. It makes you smaller, because you realize how tiny and insignificant you are in the cosmic scheme. But it also makes you larger, because you realize you're part of a universe capable of producing black holes and conscious beings and everything in between. It makes you more humble, because you understand how little we actually know. But it also makes you more proud, because you understand how far we've come, how much we've figured out through careful observation and mathematical reasoning. I want you to carry this knowledge with you. I want you to remember, when you look up at the night sky, that there are black holes out there, invisible to your eyes, but present nonetheless, marking the places where physics pushes to its limits. I want you to remember that time is not what it seems, that information is physical, that the universe is stranger than you can imagine. I want you to feel connected to that strangeness, to embrace it rather than fear it. Because here's the secret: the deadly nature of black holes, the danger they pose, the existential threat they represent, is part of what makes the universe beautiful. A universe without danger would be boring. A universe that was perfectly safe, perfectly predictable, perfectly comprehensible, would offer no challenges, no mysteries, no room for growth or discovery. Black holes are dangerous, yes, but they're also magnificent. Their nature operating at its most extreme, most uncompromising, most honest. They don't pretend to care about you. They don't hide what they are. They're just there, doing what the laws of physics dictate, existing as inevitable consequences of gravity and mass and the structure of space-time. And we, tiny and temporary as we are, have figured out how to study them, how to understand them, how to use them as laboratories for testing our deepest theories about reality. That's extraordinary. That's worth celebrating. Let me tell you about one more thing before we wrap up: the far future of black holes. We've talked about how they form, how they behave, how they die through Hawking radiation. But let's zoom out to truly cosmic timescales, scales that dwarf the current age of the universe by factors so large they're hard to comprehend. But let's try to grasp the scale anyway. In about 10 to the power of 14 years, all the stars in the universe will have burned out. The era of stars, the era we're living in now, will be over. The universe will be dark, cold, populated only by dead stars, planets, and black holes. In about 10 to the power of 40 years, even the dead stars will have decayed or fallen into black holes. In about 10 to the power of 100 years, even the black holes will have evaporated, leaving only a thin soup of photons and elementary particles spread across an ever-expanding spacetime, cooled to temperatures barely above absolute zero. This is the ultimate fate of the universe, as we understand it. Heat death, maximum entropy, a state of perfect equilibrium where nothing interesting can happen because there are no energy gradients left to drive processes. And the final act of this cosmic drama, the very last structures to exist before even they dissolve into the void, will be black holes. They're not just the deadliest objects in the current universe. They're the most enduring, the last survivors of a cooling cosmos. There's something poignant about that, something almost noble. Black holes, these objects of destruction and danger, will outlive everything. They'll outlive the stars, the galaxies, the entire era of structure in the universe. And then, finally, they too will fade, evaporating into Hawking radiation, their information preserved or destroyed, depending on the resolution of the information paradox, and the universe will be empty. But here's the thing. We don't know if that's really the end. Maybe the universe is cyclic, collapsing and rebounding in an infinite series of big bangs and big crunches. Maybe our universe is part of a multiverse, with new universes constantly budding off from black holes in other universes. Maybe there are phenomena we haven't discovered yet that will change the story in ways we can't predict. The far future is unknowable, not just in practice but in principle, because we can't predict what discoveries will be made or what theories will be developed between now and then. What we do know is that black holes will play a central role in whatever happens. They're too fundamental, too deeply embedded in the structure of general relativity to be ignored. They're the places where our theories are tested most severely, where the gaps in our understanding become most apparent, where the next breakthroughs are most likely to occur. And that brings me to my final point, the message I want you to take away from these 3.5 hours we've spent together. Black holes are deadly. They're the most dangerous objects in the universe by any reasonable measure. They can kill you in more ways than you can imagine, from mundane crushing and burning to exotic effects like spaghettification and information destruction. They represent fundamental breakdowns in physics, places where our best theories stop working and new physics is needed. They're reminders of our insignificance, our mortality, the ultimate futility of struggling against the laws of nature. But they're also beautiful. They're elegant solutions to Einstein's equations. They're natural consequences of gravity taken to its logical conclusion. They're laboratories for testing quantum gravity and information theory in the nature of spacetime itself. They're proof that the universe is far stranger and more wonderful than common sense would suggest. They're invitations to think deeply, to question boldly, to explore fearlessly. You are living in a universe with black holes. That's a profound fact, one that should fill you with awe and wonder and perhaps a little existential dread. But it should also fill you with curiosity, with a desire to understand, with an appreciation for how far humanity has come in making sense of the cosmos. 100 years ago, black holes were theoretical curiosities. Today, we've photographed them, detected their gravitational waves, tracked their effects on surrounding matter, and used them to test our deepest theories about reality. 100 years from now, assuming humanity survives and continues to advance, who knows what we'll have learned? We might have a complete theory of quantum gravity. We might have found ways to observe the interiors of black holes. We might have discovered new types of black holes or new phenomena associated with them. We might have learned that everything I've told you in this video is wrong, that black holes are even stranger than we currently believe. And that's exciting. That's what makes science worth doing, what makes exploration worth pursuing, what makes life worth living. The universe keeps secrets, deep and profound secrets, and black holes are among the deepest. But we're learning how to ask the right questions, how to design the right experiments, how to think in the right ways to slowly, painstakingly tease out answers. You're part of that story, you personally reading this. You might not be a physicist or an astronomer. You might never work on black hole research. But by learning about black holes, by expanding your understanding, by sharing this knowledge with others, You're participating in humanity's grand project of understanding the universe. You're keeping the flame of curiosity alive. You're refusing to accept ignorance when knowledge is available. And that matters. It matters more than you might think. Because the alternative is to go through life without wondering, without questioning, without looking up at the sky and asking, what's out there? And that would be a tragedy greater than any black hole could cause. So here's what I want you to do. The next time you're outside at night and you can see the stars, look up. Find the constellation Sagittarius if you can. Know that somewhere in that direction, about 26,000 light years away, there's a supermassive black hole with the mass of 4 million suns sitting at the heart of our galaxy, invisible but present, deadly but distant, a monument to the extreme physics that governs our universe. And then look at all the other stars, and remember that many of them will end their lives by collapsing into black holes. Remember that the atoms in your body were forged in stars, and that someday, trillions of years from now, those atoms might fall into a black hole, their information preserved or destroyed, their story ended or transformed in ways we don't yet understand. Remember that you are made of stardust, living in a universe full of black holes, on a planet that's improbably suited for life, in a cosmos that's vast and old and strange and beautiful. Remember that you are part of something larger than yourself, something that existed long before you were born and will continue long after you die, something that includes stellar nurseries and supernova explosions and galaxies and black holes and everything in between. Remember that you are here, now, aware, thinking, learning, growing, part of the universe's attempt to understand itself. And remember that black holes, deadly as they are also reminders of how far we've come and how much further we can go. Thank you for spending this time with me. Thank you for caring enough about black holes to watch a 3.5-hour video about them. Thank you for being curious, for being willing to grapple with difficult concepts, for being part of humanity's ongoing conversation about the nature of reality. I hope this has changed how you see the universe, at least a little bit. I hope you'll remember this the next time you look at the night sky, the next time you hear about new astronomical discoveries, the next time someone mentions black holes in a casual conversation. And I hope you'll share what you've learned. Tell your friends about black holes. Tell them about event horizons and singularities and information paradoxes. Tell them about how strange the universe really is, how much stranger than they imagine. Spread the wonder. Spread the curiosity. Spread the knowledge that we live in a cosmos full of mysteries, and that some of the deepest mysteries are locked inside the deadliest objects in existence. Black holes are deadly, but they're also invitations. And I hope you'll accept the invitation to keep learning, keep questioning, keep exploring. The universe is waiting, and it's far stranger than you think.